Long before sensors, satellites, and scientific treaties defined the boundaries of what humanity dares to test, the ocean's deepest corridors existed as realms of myth. They were spoken of as if they were fractures in the planet's memory, places where light falters, pressure reigns, and time seems to hesitate. Among these sunless landscapes sits the most dramatic descent on Earth, the Challenger Deep, a narrow depression carved into the western Pacific. It is not merely a deep place. It is a domain where the familiar rules of the surface soften into something alien. The idea of releasing a colossal thermonuclear device into this environment feels like a question born from both curiosity and unease. The device imagined for this scenario is not hypothetical. It is modeled on the most potent nuclear explosion humans have ever produced. Its energy output, measured in tens of megatons, was once recorded rippling around the globe, evidence that its shock was not local but planetary. And yet, despite that extraordinary power, its relationship to the natural forces that sculpt the Earth is strangely modest. To understand why, one must first picture the abyss itself. The descent into the trench is a gradual surrender of the world we know. At a few hundred meters down, the last scraps of sunlight dissolve. At several thousand meters, the weight of the sea becomes an incomprehensible physical presence. An unbroken column of water pressing with a force that would crush steel were it not specially prepared. By the time one reaches the full depth, pressures climb to levels comparable to the interior of industrial machinery, but applied uniformly from every direction. Life exists here in quiet defiance of expectation, shaped by a stability that the surface rarely experiences. In this environment, a nuclear detonation is not simply a larger version of one on land. It becomes a contest between a brief burst of human-made energy and the vast, ancient volume of the ocean itself. The bomb's fireball cannot flare freely into the sky. Instead, it must carve out space within a medium that resists its expansion with relentless strength. It is this confrontation, the transient heat struggling against the immovable weight of the deep, that defines the physics of what would happen. It is tempting to imagine that such an event would awaken planetary hazards, tsunamis galloping across basins, continents trembling, volcanic chains roaring alive. Popular speculation often treats the deepest ocean as a trapdoor to catastrophe, as if tampering with it might jolt the planet from its equilibrium. But the Earth is not a fragile machine with a single point of failure. It is a system that has endured asteroid strikes, super eruptions, and tectonic collisions, each carrying energies that dwarf anything humanity has built. And so the question becomes less about whether the explosion would break the world, and more about how the world absorbs it so quietly. The answer lies in the deep's ability to swallow extremes, not by magic, but by physics. The next section follows the detonation itself, tracing the evolution of heat, pressure, and shock in a place where ordinary intuition no longer applies. No sunrise, no volcanic flare, no meteor strike has ever illuminated the floor of the Challenger Deep. It is a place defined by perpetual darkness. Yet in this thought experiment, the first act is a sudden, silent ignition, a miniature star forming where light was never meant to gather. In the earliest fractions of a second, the device releases its energy in a surge so rapid that the surrounding water cannot immediately respond. The molecules nearest the core are thrust into a state no natural ocean has ever produced, vaporized, ionized, and hurled outward in a brief incandescent sphere. The fireball that emerges is not a stable object. It is a temporary victory of temperature over pressure, a bubble carved out of water by brute force. But unlike a blast in the open air, where expansion faces little resistance, this bubble grows into an environment designed by sheer mass to push back. 11 kilometers of seawater overhead create pressures that rival the operating conditions of deep industrial systems. Against that background, even a megaton-scale detonation becomes an event that must negotiate its existence. As the fireball expands, it displaces the water around it with surprising efficiency. The water does not explode outward like debris on land. Instead, it flows, folds, and compresses, transmitting the shock as a rapid pulse through the surrounding trench walls and basin. Seismic instruments would detect this pulse as a distinct but brief signature. Marine animals, especially those with sensitive pressure organs, would experience it as a violent and disorienting concussion. But the ocean itself absorbs the shock, the way a mattress consumes the force of a thrown object, quickly and without lasting deformation. Meanwhile, the fireball's fate is sealed by the environment that surrounds it. Expansion requires energy, but every centimeter outward demands pushing against pressures so immense they seem geological rather than fluid. The bubble reaches its maximum size far earlier than it would in the atmosphere. Then, as its internal energy diffuses, the surrounding water asserts its dominance. The bubble contracts, like a lung surrendering its final breath. It rebounds once or twice, oscillating between expansion and collapse, but each pulse grows weaker as heat dissipates and pressure overwhelms structure. Eventually, the bubble fragments, a shattering more than a disappearance. What was once a coherent sphere becomes a swarm of smaller pockets of hot, contaminated vapor rising slowly toward the surface. They travel not as a violent column, but as a disordered plume pushed upward by buoyancy, not momentum. The water around them remains startlingly unaffected, aside from localized turbulence and a transient increase in temperature. From above, the event would barely register as a disturbance. There would be no towering dome of water, no continent-sized wave unfurling across the Pacific. Instead, a modest upwelling might wrinkle the surface. A vessel in the vicinity would notice agitation, perhaps a brief surge. But nothing about the scene would suggest that one of the most powerful devices ever built had just ruptured the darkness far below. The spectacle ends quickly, though its implications linger. The deep, it turns out, is not a stage for cataclysm. It is a reservoir of such mass that even extraordinary violence becomes a fleeting expression of physics, not a rewriting of Earth's story. In the next section, the aftermath unfolds. The fate of the radioactive plume, the limits of induced geological effects, and why the ocean's vastness neutralizes fear more effectively than any protective system humans have engineered. Once the fireball collapses and the plume of heated vapor begins its ascent, the event enters a different phase, less spectacular, but crucial to understanding why such a detonation fails to reshape the world. The ocean absorbs heat the way a forest absorbs snowfall, slowly, evenly, and with an almost indifferent patience. What emerges is a warm, radioactive column rising like a faint ghost toward the surface. It carries isotopes of bomb material, dissolved particles of altered seafloor, and salts thrust briefly into a state of high energy. But dilution begins almost immediately. Water masses at this depth circulate not through open currents, but through slow, dense motions governed by temperature and salinity. As the plume rises, it unravels into the surrounding sea, trading intensity for breadth. By the time it nears the mid-water zone, it has already lost most of its force. The ocean is too large, too restless, too layered for the contaminants to remain focused. Within days, the chemical signature becomes dispersed across hundreds of kilometers of water. Within weeks, the most detectable traces drift into circulation paths that eventually root them into the broader Pacific. Radioactivity, however, is not the only concern in popular imagination. The real anxieties orbit larger possibilities. The idea that a nuclear event might disturb geological structures, awaken dormant magma, or throw tectonic plates into turmoil. These ideas persist because tectonic boundaries carry mythic weight. They are portrayed as fragile seams, as if a single misguided strike could tear the entire planet open. But geology does not respond to isolated impulses with theatrical shifts. It answers only to the slow accumulation of vast forces over centuries. At the depth of the trench, the detonation would indeed vaporize sediments at the site of impact. Soft layers might melt into glass-like fragments, and some rock could fracture under the abrupt rise in temperature. Yet these changes are microscopic relative to the region's natural behavior. Plate boundaries routinely release the energy equivalent of multiple nuclear detonations through minor earthquakes that few people ever feel. A blast, even one of megaton scale, introduces a jolt dwarfed by the planet's own daily rhythms. Volcanic systems remain similarly unperturbed. The pathways that feed magma into volcanic arcs lie far deeper and are driven by slow chemical and thermal processes. Triggering an eruption would require altering pressure and heat across volumes of rock vastly larger than anything a nuclear device could influence. The detonation is a pinprick against a mountain. It leaves no systemic imprint. And as for the planet's orbit, no mechanism exists by which a terrestrial explosion could alter it. Earth's mass is so immense that even the combined output of every nuclear test in history amounts to less than a whisper against its momentum. The energy released redistributes heat, pressure, and motion locally, but the net impact on the planet's cosmic path is exactly zero. The world neither stumbles nor shifts. It continues its course as if the blast never happened. In the end, the aftermath reveals a sobering truth. Humanity's most forceful inventions remain small against the scale of natural processes. What lingers is not destruction but perspective, a reminder that our power, while frightening to us, dissolves quickly when measured against an ocean's patience or a planet's inertia. The final section turns from physics to meaning. What such an experiment suggests about human ambition, our relationship to the deep, and why the ocean's silence offers an unexpected kind of instruction. Contemplating a nuclear detonation at the bottom of the ocean offers more than a physics lesson. It invites reflection on the dynamic between human ambition and the stability of the natural world. The trench is an environment shaped by pressures and temperatures that would annihilate the instruments we rely on for exploration. And yet, life has found a way to persist there, in quiet ecosystems adapted to scarcity and constant darkness. Against this backdrop, the notion of inserting an engineered burst of heat and radiation becomes an emblem of our tendency to test limits simply because we can. If the detonation demonstrates anything, it is that human power is profoundly localized. We can scorch landscapes, level cities, and influence climate patterns through sustained activity. But singular acts, even extraordinary ones, rarely echo beyond the contexts that contain them. The ocean's abyss is one such context. It is not a void waiting to be filled. It is a physical architecture built from density, mass, and time. No matter how violent the blast, the deep remains defined by the weight above it and the equilibrium it has maintained for millions of years. This perspective challenges the common assumption that the Earth is easily tipped into chaos. Much of modern fear is built on imagery rather than scale: towering waves, ruptured coastlines, continents buckling. But when the actual numbers are examined, energies released, masses displaced, pressures involved, a humbler picture emerges. The ocean is not a powder keg beneath our feet. It is a stabilizing influence, absorbing and redistributing perturbations with a steadiness that has allowed life to flourish at the surface. And yet, there remains a human impulse to dramatize the unknown. The trench, like outer space, draws attention because it lies beyond daily experience. Depth and darkness invite speculation. Catastrophe becomes easier to imagine than complexity. But the reality illuminated by this scenario is quieter. Even our most intense technologies cannot easily force the planet into a narrative of upheaval. The world is not indifferent in a moral sense, but in a mechanical one. Its systems operate on such vast scales that the disturbances we consider enormous are, from a geophysical perspective, simply brief fluctuations. The consequences that do arise, localized contamination, short-lived thermal shifts, pressure waves that dissipate into nothing, reflect a tension between human capability and environmental magnitude. They are reminders that while we possess the ingenuity to split atoms and release their energies, we do so within a framework defined by forces older and larger than our species. The ocean's ability to swallow the blast says less about the bomb than about the planet it occurs within. There is also a philosophical undertone that becomes difficult to ignore. Perhaps the deep does not merely absorb shock. Perhaps it teaches proportionality. The immensity that shields Earth from a catastrophic chain reaction is the same immensity that shielded early life from cosmic hazards and geological violence. The trench, often imagined as hostile, becomes evidence of the planet's resilience. Its darkness is not a threat, but a buffer. When the thought experiment ends, what remains is a shift in scale. Humanity's strongest weapon, unleashed in one of Earth's most extreme environments, produces barely a trace in the global record. The event fades almost instantly into the background noise of the planet's natural rhythms. This does not diminish the weapon's destructive potential on human terms. Far from it. But it underscores a quiet truth. The Earth is shaped by energies and masses that lie well beyond our reach. What we learn from the deep is not fear, but context. And in that context, even our most dramatic creations are temporary sparks passing through an ancient and indifferent sea.